Hi and welcome to video 3 on this series on the second derivative, and this is from Unit 4, Topic 1 of the Mathematical Methods curriculum. And we're looking at an introduction to optimization today, but some of the really finer details that you need before you really start the optimization topic proper. So let's talk first of all about minimums and maximums and what they mean. We've been calculating them anyway, but we now have global and local minimums and maximums, and it's important to recognize the difference between the two. So take this cubic, x cubed plus 2x squared minus 8x, and I've got it sketched there from Desmos, and I've also got the x-intercepts labelled. So you'll notice here with this cubic that we have two local minimum maximums, local maximum and local minimum. But because it's a cubic, even though this is a local maximum here at, I don't know what's that, about negative 2.5, if you shoot along here, you'll see that it does get surpassed later on in the function. So this is actually higher than that. So therefore, this is not really a maximum in the sense of some particular context you might come across. The maximum instead is up here. So let's say we're talking about a profit function. Yeah, you might build a company that gets to this point in terms of profit, but then you might make a change to the company or the structure, or you might do an expansion, and initially that expansion costs you some money, so you go down into the negatives again. Now you owe money. But then it pays off doing that expansion. All of a sudden you're making more money. Do you want to stop there? Not really. Your company has found a way to increase its growth or increase its profits and profitability, and it takes an initial investment first. And that's just one particular context. That's why local maximums and global maximums, or local minimums and global minimums, are an important feature of considering the second point, or the second derivative. So, can we determine the exact values of the local max and min? Yes, we can, because the locals will be either a value within a restricted domain, which I'll show you in a minute, or they'll be those maximum minimum stationary points. And we do that using calculus. First derivative equals 0 will give us a stationary point, because of course we can see here the gradient at those points is 0. Can we deduce the value of the global max and min for the domain -1x to 3? Let's have a look at that. I'm going to do some rubbing out because I've completely ruined this diagram. And consider that domain that I've just suggested. I've just rubbed out too far. So within that domain I've just suggested, -1 to 3, let's see what we can work out. So here's -1, and here's 3. So what we do have is we have a local minimum, and this is also our absolute minimum within that domain. So I say within x is greater than or equal to -1, less than or equal to 3, we have an absolute minimum, which is also our local minimum, and it's equal to -5. So that works. And then we also have our maximums. Now there is no, if you did the derivative here, you wouldn't find a turning point that is a maximum within this set domain. So as soon as we don't have that, we know what this thing looks like. So instead we're going, well, where could the maximum occur? Now it wouldn't occur here, because obviously if you go a bit further it's a bit higher. And because we've got no stationary point, it never actually starts to go back down. So higher, higher, higher. And the same over here, higher, higher, higher. So it's going to be either there or there. Now I've got the graph in front of me, you might not have the graph in front of you. So if you test those points, so if I just calculate y at -1, and y at -1 I can see is about 9, and y at 3, and y at 3 I can see is about 21, just reading that off the graph, then that gives me an indication of which one is going to be my maximum. And because no stationary points have occurred, apart from this minimum between -1 and 3, well then the maximum must be one of the endpoints of my domain, and therefore in this case I've just proven it's 3. Y3 is my absolute maximum. So there's some analysis for you on minimums and maximums. Generally speaking, a local min-max are either, or they're typically turning points. The global maximum minimums, aka the absolute maximum minimums, are either infinity or negative infinity. It's pretty common, as you would have seen in the cubic we just had. Or perhaps a stationary point. So if you're talking about a quadratic, it would go on down to negative infinity, but the global maximum would be that stationary point. Might also be an asymptote. So if you had a function that like y equals e to the x, asymptotes along here with 0, well then we have a minimum of 0. Now, technically it never reaches 0, but we still say the minimum is 0 because it reaches a value finitely above or infinitely above 0. Or values from the restricted domain, as you've just seen, if we have a restricted domain. They're the 4 areas that you might get local and global minimums and maximums from. Let's have a look at example 1. Determine the absolute max and min for the function f of x equals e to the 2x minus 2. So, e to the 2x minus 2, let's sketch it. I can tell you it looks something like this. E to the 2x, well e to the x actually, looks like this. And e to the 2x is just, I'm doubling each x value. This is a compression all along the x-axis. So it's inside the function. So it's in green and it compresses along the x-axis basically by a factor of a half. So it'll look like that. And then that minus 2 will just shift the whole thing down. So here's, that's minus 1 because that was 1. But now instead of asymptoting at 0, it asymptotes at minus 2. I've missed that dot point, but let's just assume that never happened. Should get a bit steeper too. So look, I'll tell you what, here's my second chance. So it should be the same as the green one, but shifted down. So there we have our y equals e to the 2x minus 2, approximately. There's an asymptote here at negative 2, and so the absolute minimum is equal to negative 2, and the absolute maximum is equal to infinity, because it goes up to infinity as it just keeps on going, but it only goes down to negative 2 because that's where it asymptotes. So that's example 1. Let's have a look at the mathematical definitions very quickly. The global or absolute maximum is m such that the function f of x is less than or equal to m for all x within a restricted domain, which might be just all x. The global absolute minimum is n such that the function f of x is greater than n for all x within that restricted domain. So just take some time to think about it. If I've got a function here, let's do something weird and wonderful. Then we might say that the global maximum is here is m because the function is always below m, and the global minimum is here because, let's just make this, because the asymptote's there, and that's n. So it's always between n and m. And n and m could be infinity or negative infinity or both. Let's have a look at example 2. For the function y equals 5x log x plus 2, determine the absolute maximum and minimum for y in the domain x exists between 0 and 2. So this function is going to look like this, but we only care about 0 to 2. The rest we don't care about. And there's my y value. So you can do some work sketching that. We could even use a second derivative test to work out stationary points, points of inflection, x-intercepts, y-intercepts, etc. But for the sake of doing this, I'm going to demonstrate to you my previous work, and that is that it goes from here and it goes to a point here which is 1 on E, and there's a minimum at 1 on E, and it goes like this, and then it goes up and actually goes a little bit higher on this side. So it looks like about that, and this is 2. So if you sketch that, you might be in a tech active exam, you can sketch it in a calculator or whatever, but there's my information, and that tells me that because of that information, the minimum occurs at x equals 1 on E, and so I get y is equal to 5 times 1 on E times log of 1 on E plus 2, and that's equal to log of 1 on E is log of e to the negative 1, which is negative 1, so it's 2 minus 5 on E, whatever that is, and the maximum occurs at x equals 2, and so y is equal to 5 times 2 times log of 2 plus 2, which is 10 log 2 plus 2, whatever that value is. But you can see we've used a graph there to get a bit of an idea of what's going on with this shape. And I would encourage you to have a little play with this concept here and maybe sketch that graph and see if you get a similar thing to me using the second derivative test from previous lessons. So there we have it. Our global or absolute minimum and maximum within a restricted domain, or maybe not within a restricted domain, and how we assess those. All the best.